Come on, recording. There we go. But it was your message making my phone buzz that made me think about it, so thank you. So, recording, cool. So recursive definition. So in section 3.1, we talked about recurrence relations and how they kind of defined these sequences. And we're kind of going to build on that idea into a more kind of general situation than just with these recurrence relations, because essentially what we're going to do today is, up to this point, we've essentially been working with these kind of function ideas, and now we're going to move into a bit, they're not necessarily going to be numbers, they're going to be ideas kind of deal. But in 3.1 and 3.2, we had these recurrence relations, and remember they have their two parts. They have the base case and then the recursive step. So we're going to have that same kind of idea here. So in everyday English, if I say the word object, it's going to mean a physical thing. You can describe its appearance and qualities and anything that it does and anything about that object. In computer science, when we refer to an object, it's an instance of a class, and again, it can be described by its variables. So we kind of have it's a set of things, and we can describe it by its variables, what it possesses, what is inside that object, and what it does as well. So it's kind of like a collection of things, kind of like the idea of a set. And we're going to use the word object similarly to both of these contexts. So an object. So an object is something such as a variable, a function, a mathematical structure that we want to describe. Essentially anything that we do to talk about what it looks like, what it does, how it, performs in a way. That's probably not the best way to say it, but essentially anything that we want to describe kind of how it works. We're going to use the word object. So if we give a recursive definition of an object, so say we have an object where it kind of starts in one spot and then has this kind of recurrence idea to it, we would of course need to define this object in two parts. As with all recurrence ideas, we would need to essentially define that base case, so a base case, which would be describing the simplest object. And then of course the recursive case, which would be defining a more complicated object in terms of a simpler one. Let me pause here for a minute to let y'all catch up, especially in case you didn't get the notes up yet and are trying to write this down from scratch. One thing I'll say though, as you catch up, is in this section, we're going to kind of use this B and R to refer to our base case versus our recursive case. So we're essentially going to be defining things in terms of base case and recurrence, recursive cases, and we're going to label them B and R. Because again, we're not going to have them necessarily in like that function notation type of idea that we were looking at already. It's kind of going to be a more generic setup to allow us to do a lot more than just work in a function sense. And you'll probably see what I mean in a second. So hold on a couple more seconds. And then the first one we're going to look at is actually one of the ones in function notation. But essentially we're going to kind of take this function definition and rewrite it in kind of this new form of kind of just a generic setup. It's lagging very much. So essentially, this was an example we did back in 3.2, where we had this function where it starts at 5, and then you essentially just add on 3 in each case. And so if we wanted to take this kind of recursive function, this recursive relation, and write it as a recursive definition, there's kind of two ways we could do it. I'm going to do it one way. I'm going to do it both ways. The one of them is kind of the easiest to kind of see the jump from, and then the other one is a bit more of the normal notation we'll use. But so again, we need to define essentially a base case and a recursive case. So we'll write that as a B and an R instead of writing base and recursive out the entire time. And so essentially, if I wanted to do this in somewhat similar notation to this, I would write that P of 1 is 5. Like I would have to tell them where we were starting at. And then to write the recursive step, we need to be kind of specific. We would need to say for any n greater than 1, we kind of have to take into consideration this piece from the recursive. P of n equals 3 plus p n minus 1. Now you might think that this just looks like we're rewriting it. That is essentially what we're doing here. But let me come off over here really quick. So essentially what we're doing is we're changing from function notation to kind of descriptive cases. And that's the difference between a recurrence relation and occurrence definition. That one's lagging a lot. That one's not. Catch up with me, other computer. But I'll keep talking. So essentially the difference between a recurrence relation and a occurrence definition is a definition uses a lot more words and it's a bit more descriptive than just saying here's the function notation. Now that's kind of notation that probably makes the jump seem the easiest, but it's not usually the format we're going to really phrase these in. So let me also write this again in a bit more of the normal notation that we'll use. And I'll hold on a second because that I don't know if yours was lagging as much as mine. So just in case, I'll hold on for a second before I do that. Especially because it's still lagging a lot. Let me reshare my screen and see if that helps. And now that one's lagging. It's so funny. You got this. Oh, I didn't reshare it. I'm an idiot. So kind of the more normal way, not normal, but the more notation we'll use here is we'll say something like we're going to define, how do I want to phrase this? We're going to say a recursive definition. So I shouldn't have written this yet. So a recursive definition for a set X. We're usually going to write these kind of in terms of thinking of them almost as sets. And you can kind of think of this recursive relation as like a set of numbers. So essentially what we would say is we would tell them one thing that is in that set. So in this case, we would be starting at 5. So we would say that 5 is in that set that we're describing. And then how do we get from that one thing to anything else that's in the set? We would take that thing, something in the set, and add 3 to it. So essentially we would say that hold on one second. Sorry, I should have had something first. We need to say if we have some element in that set, then that element plus 3 is also in that set. Which is essentially what that recursive relation is saying, is that we're saying we're taking anything that's in there and we're taking the previous term and adding 3 to it. So this way is essentially another way to say that, but also not necessarily say that it has to be directly the term before it. Like there's no more term before it kind of idea with these recurrence definitions. It kind of takes that piece away, but it's still going to give us the exact same set. It's still going to start at 5. And essentially everything that we can create has to start at 5. So I have to start with 5 because that's the only thing that I have in the set to start with. Once I start with 5, I can get 8 and 11 and 14 and so on and so forth. So that's kind of, this second way is kind of more of the normal notation that we're going to use, where we're going to say, here's something that's in the set. Here's how you would find anything else in the set from that thing kind of idea. So, same kind of idea of these recursive things. We're just describing them in a bit more of a descriptive way than just saying, here's this function notation. So, I don't see any questions, so I'll move on. If you have questions, let me know. So how are we going to work with these recursive definitions? Well, if you think about when you learn to read, if you can remember when you learned to read, I really can't. We, usually start with individual letters. You learn what all the letters are and their sounds, and then you start actually putting them together to form words. And there's a kind of similar thing, of course, in computer science where you have a list of symbols, but we call something a string. You'll have probably heard this before in your life. A string is a sequence of symbols written together. So you can think of like the letters as the symbols and the words as the strings. So for example, something like cat would be a string, or maybe you even don't think of it as the word cat, you just think of it as CAT. But then you can also have a list of symbols, so AS $7 plus sign is a string. Absolutely any, sequence of any symbols I want to string together would be a string. String together. And we can also have the empty string, which of course would just be nothing. So that's another way that we're going to be using these recursive definitions, is a way to use these strings, because you can't really write out anything with strings in terms of a function notation. So we need some kind of descriptive way to tell ourselves how we're going to form these things. So say we're given the following. We're going to be given a list of symbols, some a sub 1 through a sub m. And that's going to be a string. And we're essentially going to define this recursive definition to be, now here, notice we have B1 and B2. We have two base cases. That's perfectly fine, okay? That's essentially what happened with the Fibonacci sequence, is that you were told that the first term was 1 and the second term was 1. So it's okay to have more than one base case. So here, what we're told is that the first base case is that the empty string, which we're now going to denote by lambda, so that we can at least know that we're talking about the empty string without having to write nothing. So we can have the empty string, which we're going to say lambda, or we can pick a symbol, some a sub I. So those are our two base cases, either the empty string or a single symbol. And then the recursive case is we can essentially get some xy, which is going to be the concatenation, which is just writing the things next to each other, of two symbols x and y. Now, sorry, I just said symbols x and y. X and y can also be strings. So x and y's can be symbols because singular symbols are strings, or they can be, strings of multiple symbols as well. And we can essentially form a new string by taking those two strings and concatenating them together. So that's what the recursive definition is telling us. It's telling us that we either have to start with an empty string or a single symbol, and then essentially after that, once we have two strings, we can smush them together to make a new string. So as I already said, lambda is going to have, represent the empty string. It's not written after it has been concatenated with another string, so we wouldn't really write CATS lambda, you would just write CATS. Now, if you want to write it in general at first in part of a step in one of these recursive definitions, if you want to write a lambda at the end of something, that's fine. But then you want to simplify it one step further and just say, okay, then that lambda can essentially go away. Now we can also essentially add in lambda whenever we want, because having an empty string somewhere isn't really changing anything about the string because you're adding in nothing. So we can also kind of add in empty strings wherever we want. But anyway, so we want to use the lowercase English alphabet as our set of symbols. And we want to explain why USB is a string, essentially justifying each step with an appropriate part of the definition that's above. So we essentially want to take this recursive definition and use it to be able to explain why we can form USB as a string. So we have to do this kind of very kind of step-by-step kind of deal. You have to break it down into its very smallest pieces. So what's the first thing we need here? Well, we kind of need each one of those singular symbols. So if I want to start forming USB, I should probably get a U. Well, I can get that U as a string because a single symbol is a string, but that's essentially using that second base case, because base case 2 tells us that any symbol just by itself is going to be a string. So I can say that U is a string. Well, I need to start building USB, so let me get some of the other letters. So I know that S is a string, also by that second base case. Now, if you wanted to, you could jump ahead and say that B is also one and then go from there, but I'm going to take a step before I introduce B. I'm going to go ahead and say we could concatenate these together and get US is a string by R. We took those two strings and concatenated them together, and we're allowed to do that because our recursive step tells us we can. And so while I want to still create USB, so we need to essentially allow B to be in existence. So we have that B is a string by that base case. String. And now I can essentially finish it off because I have US and I have B. So if I concatenate those two together, I can get USB. So USB is a string by that recursive step. Now, one thing is that we would need US before we can jump to USB. So you can't just say U is a string, S is a string, B is a string, USB is a string, because the recursive step only takes two strings. So you can't take U and so separately, U separately S separately B, those three separate strings, and string them together using R, because the recursive step only tells you how to do it if you only have two strings. So you need to kind of create that US before you can connect it together with the B. If you wanted to be weird, you could create SB first and then concatenate U and SB. But the point is that you essentially need to take one of those kind of middle steps of stringing just two of them together and then taking that string of two symbols and stringing it together with the last piece. Hopefully that made sense. So that's kind of the idea of these recursive definitions. Is we're just going to use them to kind of, when we want to talk about something that's not necessarily numbers, this is really the best way to do so, because we can't just put it in function notation, really. We want to have some kind of descriptive situation where we're essentially telling you how you can use the symbols that you have. I don't see any questions. This is going to go way quicker than I thought it was, but that's okay. So I kind of already said this, but it's at the bottom of the page and it's kind of random in there. So note in the one we just did, there were two simplest possible strings. So we had those two base cases. So I kind of already said that. So in this case, we had to say, well, you could have nothing or you could have a single symbol. Those are like your two simplest choices. And again, it's perfectly fine that you have multiple base cases. But really, you do want to be aware that you just can't create base cases willy-nilly. They do kind of have to have a point, and they do have to be those simplest terms. So you can't just like create as many base cases as you want. They just have to be the ones that are simplest. And if in that case you have kind of two simplest choices, either nothing or a single symbol, then you have to list them both. Anyway. The next thing is, say we have S is a string, and we're going to define its reverse, so S to the R, as follows. So S can be any string, so it's the simplest situation we could have here. We could have that the simplest thing is that we have nothing, and we want to reverse it. So if we have the empty string and we want to reverse it, it's just the empty string. And then with the recursive step, the reason we don't need any more base cases is because we can have whatever strings we want. We don't need to build up the strings here. We're just given the strings. So that's why we just need that one base case of the simplest thing of if there's nothing, it's just itself, essentially. Nothing is nothing. So say we have S has one or more symbols. So I'm going to highlight that, one or more symbols. So say S equals RA, where A is a symbol and R is a string. So S is at least made up of two symbols, so it might be able to just be broken up into those two symbols. Or if it has more than two symbols, we're going to think of it as a string in the front and a singular symbol in the back, where possibly that string in the back is empty. If we wanted to reverse that string, we essentially take the very last symbol, put it in the front, and then just reverse what's remaining of the string. This is kind of like, whoops, I forgot I was still in my little highlighter. Just for notation purposes, that A is now kind of by itself, and we're just reversing the remaining string. Like, it's not that that A is still considered part of that. So we're going to use that definition to find the reverse of the string raw, and we're going to justify each one of those steps with one of the steps above. So we do need to kind of tell them exactly why we're allowed to do what we're doing. So we need to start with what they give us. So we want to find the reverse of raw. So this is a string of more than one symbol. So this is where we're going to use R. So we essentially think of this R and the A need to stick together. They're a string. And then the single element, the single symbol W on the outside. So what our recursive step tells us is that we can bring that W essentially out to the front, and then that RA is going to stick together, and I'll still need to reverse that. So this is going to be by R. The recursive step, I know there's like multiple R's floating around, the R for the reverse and the R for the recursive step label. That one's lagging a lot. Hello. Why is it just this screen that's lagging? There we go. So once we're here, we still want to keep going. We essentially want to do this until we have no more reverse. But since that RA is still two or more symbols, sorry, one or more symbols, it's two symbols. We essentially think of that R as a string. It's a string of just one symbol, but it's a string. And then we think of the A as a singular symbol in the front. So if we want to reverse that, the W still stays in front, but now that R kind of comes, sorry, the A pops out front, and we have that we still need to reverse the R, which was another use of our recursive step. Now, this is where it doesn't necessarily get tricky. It's really not tricky, but there is a tiny little trick that you need to notice here. We don't know what the reverse of R is. Like, we can't just say that that's R, because that's not part of our definition at all. So what we need to do is we need to tack, whoops, why did that W become an A? WA. We need to essentially tack in an empty string in there. And remember, we can tack in an empty string pretty much anywhere because it doesn't really change anything. It's an empty string. My one screen's lagging a lot again. Let me unshare and reshare just in case that'll help that. Again, I don't know if yours are lagging as much as mine is, but just in case, I always try to wait until mine have stopped lagging. So we add in an empty string. Now this, we don't really have a, is it? Okay, if yours is lagging any more than mine is, and I'm like still going way ahead, just yell at me in the chat and tell me to slow down, because I'm going as fast as this is allowing me to go based off of the lag that I see. But if I don't see the lag that you see, just let me know. Anyway, so this isn't really a step from the base case or the recursive case, but just to remind us why we can do this, we essentially need the empty string. Because why did we need this? We didn't know how to take the reverse of just a single symbol. So this recursive case, because the needs two or more symbols. I'm realizing that my recursive case is then what I wrote in my recursive case says one or more. Oh no, oh no, oh no. I even highlighted it, and that just makes it worse. That should definitely say two or more. Or more symbols. Because it has to have, we have to be able to write it as some RA. We're not told how to deal with it if we can't write it as some RA. So sorry, that should say two or more symbols. It needs to have at least two symbols. Ooh, that was a real big mistake. Sorry about that. Anyway, so we need to add in that empty string because that recursive step should say two or more symbols. We have to be able to write it as some RA. So we need to add in that empty string, which is perfectly fine because it doesn't change anything. But now we know how to reverse that to R because we bring that R out front, and now we have lambda reverse. And we know what lambda reverse is. That's why the recursive step should say 2 or more symbols, because we can figure out what lambda R is because that's our base case. So we do know how to handle that. That's the other way reason why I had to write lambda R and not R lambda, because if I wrote R lambda, what the recursive step would have done is brought the lambda out, and then I'm still back at trying to reverse R and not knowing how to reverse R. But, so this was by a recursive step. And then we can say that lambda reverse is just lambda, which you don't need to write at the end of anything, the empty string by the base case. Well, let me write lambda, and then I'll take that last step to be getting rid of the lambda. So that's how we reverse a string. And I know that, you kind of realize what's going to go on immediately. You just flip the word around. You just flip the string around. But that's how we would have to write it out in its steps. And if you think about like what code is doing and how very meticulous you have to be with code and all that jazz, you usually have to tell it, at each step you do this. You might not have to see all the steps that it does, but that's technically what, some code would be doing if you were telling it to reverse something. You can't really just say, flip it around. You would have to say, move that over, move that over, move that over, move that over. Anyway. Questions, concerns on that? All righty. So, say we go back to the idea of trying to write these recursive definitions. So we want to take a set of things that we're told, this collection of objects, and we want to try to write a recursive definition for it. So say I want to give a recursive definition for the set X, which is going to be all positive multiples of 3. So note. Oh, lambda? Yeah. I mean, I don't do a lot of computer science stuff, so. But I know lambda can be used for a lot of different things. It is often used for wavelength, yes. But essentially it's just a variable, so we can tell it to be whatever the heck we want it to be, and in this case we're using it for the empty string. But anyway, so we have that. Note that X is 3, 6, 9, 12, 15, blah 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 blah. They didn't necessarily need to, start writing out that set for us, but they're trying to help us out a little bit. So if we wanted to write a recursive definition for this, well, we need a base case and a recursive case. Remember, the base case is essentially in that set. So essentially we kind of want to think of it as the smallest positive multiple of 3, which would be 3. So we would say that 3 is in this set. And now the thing with the recursive step is you don't want to necessarily think about it as a function. You want to think about it as taking something that's in your set, and how do you take that thing and use it to find another thing in that set. So we would essentially have to say, how can I take this element 3 and create another element, such that I could take that element and create another element, and so on and so forth. So here we would essentially say, if some little x is in our set, then you can, again, it's not necessarily that you need to think about it as one term to the next, like we were doing with the recursive relations, but that is one way to try to help yourself figure out what this should be. So how do we get from 3 to 6? Well, we would technically, there's a couple ways. You could multiply by 2, or you could add 3. But if you then think about getting from 6 to 9, multiplying by 2 is now out. So we would say that to get essentially from one term to another term of the set, we would want to add 3. So let me just make a little side note here. You need a way to build up to new elements. from those that are already there. So like if you were to read positive multiples of 3, you might originally think of 3 times something, which is a way to describe multiples of 3, but if we want to describe it in this case, we need to get from something we already have to another multiple of 3. So we would need to take that thing that we already have and add 3 to it. So it's not just that you have to describe the situation that you're in, but you also have to describe it based off of a thing you have. You have to start with something you have and get to another thing that you want, if that makes any sense. So recursive definitions are not limited to strings and numbers. In 3.1, we looked at binary trees. Those little, things that we did binary search trees, but those are a very specific case of a binary tree. And so we could also define a recursive relation for binary trees. So it's not just something that has to be numbers. It's not just strings. You can kind of do these recursive definitions for a lot of different things. And that's kind of their point, is that they allow you to do this kind of recursion with a lot more stuff than we could before. So say I wanted to give a recursive definition on the set of all binary trees. So remember, a binary tree is essentially a tree where each piece only has 2 children. So you go to the one vertex, you can only go down 2 directions. You don't have to go down in both directions, but you can't go down 3 or 4 or 5 directions. So each only has possibly 2 options. But anyway, so let's think about describing all binary trees. And we kind of did something, we kind of got into this idea a few sections ago. We talked about a recursive relation for finding the number of vertices in a complete tree, a complete binary tree. And remember, we were looking at the fact that if you take 2 binary trees and shove them together, you get another binary tree. That's the same idea we're going to use here in kind of our recursive step. But let's think about the smallest binary trees we could have. So what's the smallest binary tree we could have? Well, there's kind of 2 cases. We're kind of in a situation where we have 2 base cases again. Because technically, we could have nothing. So we could have one base case where we have essentially the empty tree. So the empty tree is a binary tree. It's kind of a very silly binary tree, but it technically is a binary tree, just like the empty string is technically a string. But there's also another kind of simplest tree where we could essentially have a single vertex. And once we get past those are kind of our 2 smallest cases, and everything else can be built from those 2. So we have a second base case for a single vertex is a binary tree. And the vertex is the root. I just say that because we're going to need to be talking about how to put these together based off of roots. So I want to say that in terms of that singular vertex, that single vertex is also considered the root of that tree. And remember, the root is kind of that top vertex that everything stems out of. So what would our recursive step be? Well, this kind of goes back to, again, that idea of if you take 2 binary trees and kind of connect them at a new root, then you have a new binary tree. So essentially, if, let's say, T1 and T2 are binary trees, with roots, let's call them R1 and R2. So we have these 2 binary trees, and each one of them will, of course, have a root. Then the tree, which we're going to kind of draw here, well, not really draw. So we have some kind of, tree here, and it's going to have its root at R1. Just imagine the thing inside that circle is with these roots. Essentially, if we connect those 2 roots of those trees to a new root, it makes a new binary tree. So this tree is a binary tree. I shouldn't have put a period there. It's a binary tree with root R. We're essentially adding in this new root and connecting the two original binary trees to it. One last thing I should write in here is just a kind of clarification in what could happen when we connect these two trees. So if either of those TIs, so either T1 or T2, a little bit of lag. If either one of these original trees we were using is the empty tree, there is no edge from that tree to R. Essentially, it's just saying that if one of these pieces was an empty tree, you're not going to have just a random edge that goes to nowhere. Because if it's an empty tree, there wasn't a vertex there and you can't connect an edge to nothing. So that's just like a clarification where if either one of those two original trees, binary trees, was empty, which is okay, it's just that that edge is then not going to be there. It would still create a binary tree. It's just that we wouldn't have an edge going to nowhere. So that's just like a clarification need there. Does that make sense? So it's still this kind of idea that we're starting with the simplest pieces and we're using those pieces to build up to bigger pieces. It's just that we're now in a lot more different contexts than just numbers. That's mostly it. We got one thing to talk about, but we're not really talking about it in much detail. I'm just giving you some pretty pictures to look at. So one thing that uses recursion a lot in mathematics is this idea of these things called fractals. So fractals are geometric objects that are defined recursively. So we're not really going to do many examples with these geometric ones, but just they're kind of cool to look at. So the following would define something called, I actually don't know how to say that name, Coche? I don't know. I'm going to say Coche. I actually don't know how to pronounce that.
Coke.
Is it Coke? Coke snowflake. That sounds silly. Anyway, when the definition is implied infinitely, so K sub 1 would be an equilateral triangle. And then if you want to build any of the other things from that one, what you're going to do is you're going to replace, essentially, let me do this in a different color. You're going to replace every line segment of the thing before it with essentially, you're going to stick like a triangle without the middle piece in the middle of it. So essentially you start with an equilateral triangle and then you essentially break up all of the line segments with a little whoop whoop in the middle. And then you just keep doing that over and over and over and over again. And you could do this infinitely. I mean, drawing them, you would get to a point where you could no longer draw the little whoop whoops. But technically this could be done infinitely. And there's the shortest little video that kind of shows you how that looks like. So let me just do that really super quick. Once it pops up on my other screen. There we go. That's really funny. The video is like a tealish, and then on my other screen it's blue. Anyway, so this is essentially what happens. You take the equilateral, you blimp it, you blimp it, you blimp it again, you blimp it again. And then it does the same thing just with black this time. So that can continue infinitely. You know, we can keep doing that until our arms fall off. But that would be an example of a recursive definition that gives you this type of fractal idea. And one more fractal that's kind of cool. Scroll down. So if you want to look at that video again for some reason, there's a link. We also have a Menger sponge. I'm pretty sure I'm pronouncing that wrong too. Menger, I don't know how to pronounce people's names, is another example of a fractal where essentially you start with a cube and then you're essentially going to divide that cube into essentially 27 equal pieces. and then kind of remove the center of each face. So from the first one, from the cube to the first iteration, you essentially take that face and then you just pull out the middle. Jumping from the first case to the second case might be a bit harder to see, but then essentially it breaks it up into each one of the things that are left is its own kind of cube. And then we do the same thing where we take the middle. Oh, it's lagging a lot. But essentially, once you've jumped to that first case, it now, you think of it as being broken up into a bunch of different littler cubes. And you do that same idea where you kind of take the middle piece of each face of the cube and pull it out. Wow, that's really lagging. There it is. I was just trying to say that we break it up into other cubes and you take the middle of that cube and you pull it out. And then you do the same thing over and over and over again. And again, this could technically continue indefinitely, but it would just be really hard to draw or to notate. Notice that that third iteration of it is already looking pretty meh if you want to try to figure out what's actually going on there. But this could technically continue on as long as you want to. So those are two examples of fractals. Fractals are actually really cool, but it's essentially this idea where you're doing the same kind of idea geometrically, where you're just adding in this same kind of idea into the picture over and over and over again. There's broccoli that follows a fractal. I forget what it's called, but I used to freak out about it because it looks really cool. But if you want to look up fractal broccoli, I'm pretty sure if you Google fractal broccoli, it comes up. It's really cool. Anyway, that's me nerding out for the day. That's 3-3 though. Like that, we're done. 3-3. So the thing you want to pull from 3-3, because it will be on your exam, it's on the review as well, is this kind of idea that we were talking about where you want to be able to define a recursive definition given a set, and also this idea of these reversals. Reversals of strings will also be fair game on your exam. But oh my goodness, my English. There are a few examples of that on the review that's already up. So we still have half an hour. It's definitely not worth moving on to anything. I also haven't put any of the new notes up yet. But for the remaining 30 minutes, if anyone has any questions, we can totally go over that. If you want to leave, feel free. But if anyone has any homework questions or questions from the review or questions in general that you would like me to go over, we can do that now.
I did have a question about your uploads.
Mm-hmm.
Earlier on they were, like some of them would be like 250 kilobytes or 1 megabyte or stuff like that. And the last one you put up was 20 megabytes. And so I wanted to ask you, about if there's something you were doing different as far as like saving PDF or something.
Oh, I see what you mean. Oh, my review answers. What did I do for that? What did I do last time?
It just happened on the last two uploads. The one, when you did the first half of it, came out to be 10 megabytes. And then the second, when you finished the second half and did the complete version upload, it was 20 megabytes.
I see that. It's because I switched, well, I assume it's because I switched to OneNote. That's the only difference, is that I switched to OneNote from just doing it on Microsoft Edge, which I guess makes it heftier. That's strange to me. I mean, I could
thought
always.
It was unusual because PDFs usually aren't
Yeah,
that
that's pretty
massive files.
I didn't realize OneNote makes it that obnoxiously large. I could do one of two things moving forward. I'm not going to try to deal with the ones that are already up there, but I could just switch back to Microsoft Edge, or I could try to figure out a way to save the ones from OneNote as to not be that obnoxious. Because I see what you mean. Yeah, they bumped up a lot. But that's the only change, is that I switched to OneNote because I thought it would make things a little easier in terms of writing as opposed to Microsoft Edge. But anyway, figure that out later.
I have a quick question about the third question from the review.
Yeah.
It was I think equivalence relations, and it was asking whether it was a equivalence relation or not, I think. And then when we got to the transitive step, it didn't meet the transitive step, but I thought if there was no because you need like an A, B, and C, correct? But if all of the terms were used, you would because on the exam, or not on the example, in the in the lecture, I remember you talking about if there was no transitive there, it didn't matter in the equivalence relation or not.
Right.
I don't know
So
if that's still continued on. I was just confused.
let me pull that up really quick because I understand what you're asking, and I just want to pull this up really quick. This one. Let's just go to Edge, and then I gotta share it. Share. So this one. And then after this, Dakota, I can do that. Well, I'll have to pull it up. I don't really know what you're saying, but I'll figure it out. So I see what you're saying. So for blah, 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 for recursive, not recursive, transitive, we want, if we have A related to B and B related to C, then we need A related to C. And so in one of the things I think we did in the lecture, it was like, okay, there aren't any transitive cases. But here we actually have one possible transitive case. So we essentially need to look for something where A is related to B and B is related to C. Well, we have 1 is related to 2 and 2 is related to 4. Since those actually appear in our set, in our relation, we have a case of possible transitivity, or at least maybe I shouldn't phrase it like that. Because we have those two, for this to be transitive, we would need the third. So the thing that happened in the lecture, we never actually came out to having that pattern of A relates to B and B relates to C. We didn't have those two appearing, but here we do have one case where that appears, where we have 1 is related to and 2 is related to 4. But note, that would mean that I would want 1 is related to 4 in here somewhere, and I don't have that anywhere. So since we have these two pieces that kind of fit the beginning of the transitive statement, if you will, then we would need to have the last piece. But if you don't have those original two, then you don't need to worry about it. Does that make any sense?
Yeah, okay. Thank you.
You're welcome. So, Russell, yes, your exam is still Thursday. Isaiah, it would have to be 1-4. So notice when we are talking about transitive, it's A is related to B and B is related to C. So A has to be related to C. It has to be in that format. But so to answer your question, no, it can't be 4-1. But nope, I don't want to. Nope, that's too confusing. I will say, do remember that symmetry is kind of a separate issue. So if 4-1 was in the relation, you would also need 1-4 for symmetric. But when it comes to transitive, it needs to follow that A relates to B, B relates to C, so A relates to C. You can't flip-flop those around. Can you go over one of the sequence of difference problems from the homework? I'll need to pull one up, but I can. Website, not Wiley. And
I also had one more question on the review. You had, I think, I don't know if it was a well-defined, it was I think it was an induction, but you had like where we just filled in certain points of the question. Is it going to be set up like that?
So I haven't written your exam yet, but I would say it's more likely to be that you have to do it fully. So there is one of those, question 21 on the review is a full out one, and it would probably be more of that. I know there is that one where you fill in the spots, but I would also rather say study it as if you would have to do it on your own and then just have it end up being a blank one than saying it's a blank one and then having it be a full one. So,
Okay.
but I haven't written it yet. But most likely it will be a full one. Do you have a number for me, Dakota, or am I just finding one? Mine's being very slow, but I can try to grab one. Differences, number 14. Cool, I was about to number 14. Sure. Let me, nope, that's not what I want. I want OneNote, and then let's just get a generic page in here. So it's going to give me completely random numbers. So my numbers are not going to be the same as your numbers, but the process is going to be the same. So the numbers that it's giving me is 1, 7, 16, 101. I better write them closer together or I'm going to run out of space. So 1, 7, 16, 101, 502, 1756, 48, 27, 11, 2, 3, 6. I'm still gonna run out of space. 2, 3, 1, 9, 1, 4, 3, 7, 1. Oh man, I'm one short. And 7, 6, 7, 8, 6. Woo. So again, you probably don't have the same numbers, but process is gonna be the same. So we need first, second, third, fourth, and fifth differences. So first difference is we take, the ones that are right next to each other and subtract them. So I need my trusty dusty calculator. So we've got 6, 16 minus 7, 9, 101 minus 16 would, one moment, be 101 minus 16, 85. 502 minus 101, 401, 1756 minus 502, 1254, 4827 minus 1756. Oh, okay. I thought my numbers weren't matching their answer and I was highly confused for a second. 11236 minus 4827, 6409, 23191 minus 11236, 11955, 43717 minus 23191, 2526 and 76, 786 minus 43717. So this would be first differences. And the way you would want to write it in WebAssign is you just write them all separated by commas. And then so second differences, we just do that same thing again, where we just take the consecutive terms and subtract them. So 9 minus 6 is 3. I can do that one in my brain. 85 minus 9. 401 minus 85. 1254 minus 401. Tedious these ones are, but 3071, 1254, 1817, 6409 minus 3071, 3338, 5546, 8571, 12543. And then of course we do the same thing again. So third differences, same deal. So essentially, remember also the point of these is to essentially figure out what type of polynomial that recurrence relation or that sequence could mimic, if you will. And so we're looking for these differences to end up being constant at some point in our lives. So we're hoping that at some point these are going to turn out to be constant. So we'll get 73, 240, 539, 537, 537, 964, 1521. I'm going to just start writing the answers from WebAssign. I don't know why I wasn't doing that before. Because this piece, while tedious, hopefully isn't the hardest part of this question. So we keep going. Take fourth differences. And then fifth difference, and this is the last one they ask us to do, so hopefully this will turn into something that's actually helpful to our lives. So we'll get 130 for all of these. Now the thing with WebAssign is that you literally need to write 130 that many times. That is one thing. In WebAssign you will need to write whatever that constant number is multiple times. But anyway, so finding those differences hopefully isn't the hard part, but then it asks the question, from what degree polynomial does this sequence appear to be drawn? So remember, the point of this is to find the polynomial type that this sequence would match, and it essentially is whatever difference you're at that is constant is going to be the degree of the polynomial. So the degree of the polynomial in this case would be degree 5, which is what you would put in that last box on that question. Since the fifth difference turned out to be constant, that would mean that this sequence would follow a 5th degree polynomial. Is that good enough, Dakota? Hopefully. What is this thing? Oh, I did not mean to send that. Okay, never mind then. Yeah, I can totally see that happening, where you could, I would probably mess up too and have to do it multiple times. But if you need help, if your numbers are getting in super wrong and you're getting super frustrated, let me know and I can pull up your actual numbers and figure out which ones are off. Anybody else get any other questions you want me to do or talk about or whatever? Because seriously, I don't have anything else for you. Yeah, Dakota, if you give it another try and it doesn't work out, email me and I'll pull up your exact numbers and I'll look and see which ones are off and we'll figure that out. Because I'm sure that I would be the same way.
Can you upload that as soon as you can?
The notes or?
Yeah.
Yeah.
Just the notes for today.
They might be in an obnoxiously large thing again because I'm still in OneNote and I don't know how to make it less obnoxious, but.
Okay. Well, I was still able to email it. I was just concerned that it might be getting near the limit or something.
I get that. I'll try to figure out how to make it.
Thank you.
Not that. You're welcome. I can't figure it out. I'm just gonna do this for now. If nobody has any questions, y'all are free to go. Like I said, I don't have anything else for you today. If you have questions, ask away. But Otherwise, I will see you on Thursday. Some of the questions on the review be to the exam. Probably pretty decently similar. Again, I haven't written the exam yet. But that's kind of where I'm going to be pulling my my inspiration, if you will, is from that review. So it'll be maybe not exactly the same, of course, but if you feel comfortable with the review, you should feel comfortable with the exam.